So welcome all of you to the day 2 of IMSC 60. This is the first session of today's talk. And we'll have 4 talks in this session. And the first talk will be given by Professor Arvind. Professor Arvind needs no introduction. And he has been associated with IMSC for over 3 decades. And he has been inspiring generations after generations, including many of us here. I can say this especially to the TCS colleagues and including myself. I mean, not only has he been leading light in the academic area where he works, he has also been the torchbearer of the institute, one of the torchbearer of the institute. He was the director of this institute from 2014 to 2022. And I mean, he has a wide area of academic interest, complexity theory being one of them. And he will give us a talk on arithmetic complexity in non-commutative world. Over to you, Arvind.
Good morning, and thank you for the introduction. And thanks to the organizing committee for inviting me to give a talk at this really wonderful occasion, the 60th birthday of the Institute. I was recalling that I joined in 1993, which is slightly less than 30 years back. So roughly 50% of the life of the Institute I've been associated with the Institute here. So happy birthday, IMSC. So this topic, arithmetic complexity in non-commutative domains, is something that I've been collaborating with the large bunch of people who I've all listed down here. I just want to point out that Rajat Datta was a CMI student. He finished PhD from CMI, and he's in Bangalore. Utsav Ghoshal is a current PhD student at CMI, and Ramya is a colleague at IMSC. She is a faculty member here. And all the others were at some point of time PhD students at IMSC. And I've been fortunate to have a wonderful bunch of colleagues to discuss this topic. So I'm not going to talk about everything that we've done together, but just a select bunch of observations which ties together with automata theory. That's a kind of unifying theme for today's talk. So let me get started. So the central problem in complexity, as we all know, the holy grail is to separate P from NP. P is efficient, problems that can be solved in polynomial time, which basically means efficiently solved. And NP stands for a class of important problems for most of which we don't know efficient algorithms because they are hard in practice. And on the other hand, they have this nice property that they have efficiently verifiable solutions. So that's technically that's the reason why it's non-deterministic polynomial time. You can non-deterministically guess a solution and you can then verify that you have a solution. And we don't know how to separate P from NP. So at some point of time, there's this famous person called Les Valiant. He said, let's try the easier problem first. Can we show that the permanent polynomial does not have polynomial size arithmetic circuits? So by looking at polynomial size arithmetic circuits, we dumb down the model of computation. We don't know how to deal with general computation. It's too clever. It can look at bits of a number and can do all kinds of clever things which we don't know how to handle. Suppose we restrict ourselves to just the permanent polynomial, and the reason why he considered the permanent polynomial was because counting the number of perfect matchings in a graph or simply computing the permanent of a matrix with zeros and ones in it is as hard as any NP-complete problem. Okay, so it's in fact actually much harder. So his idea was that you take this harder problem and take a dumber model, and can you show that the permanent cannot have polynomial size arithmetic circuits? And this was posed in 1979 sometime, and we still don't know how to show that the permanent is hard for arithmetic circuits. It requires exponential size arithmetic circuits, or at least super polynomial size arithmetic circuits. So we want to make the problem easier. So why not consider the non-commutative permanent? You make the model still dumber. So you say that the variables can't commute with each other. So you can't do clever cancellations by moving around variables. So x1 into x2 is different from x2 into x1. But the permanent polynomial still makes sense, and arithmetic circuit still makes sense because multiplication is now non-commutative. In this easier model, can we show that the permanent does not have polynomial size non-commutative arithmetic circuits? This problem was posed by a person called Noam Nizan in 1991. The problem is still open, but that's the theme, and that's the reason why we are interested in the non-commutative domain. So as I just mentioned, it's also easy to prove mathematically that proving p not equal to np is harder than, it will imply that the permanent polynomial does not have polynomial size arithmetic circuits, which will imply that the non-commutative permanent will not have polynomial size non-commutative arithmetic circuits. So we should try 3 first. So just a quick background slide. We are the kind of things that objects we're interested in are polynomials. So the commutative polynomial ring is a multivariate polynomial ring. F is any field. You could take it as rational numbers or complex numbers. And the corresponding non-commutative object is the free non-commutative polynomial ring, where the angular brackets say that these variables xi don't commute with each other. A monomial is a word basically. It's a string really on the letters x1 to xn. And this is the free non-commutative ring. And back to the familiar examples, the permanent polynomial is the first one. Non-commutative means that the variables you can't reorder the monomial. Okay, this is a particular version of the non-commutative permanent. There's more than one version. We'll just focus on this. And the other one is the standard determinant polynomial, where you throw in the sign. And we know that as opposed to the permanent, in the commutative world, the determinant has efficient algorithms. Because you can do linear algebra, you can do all kinds of things. What are arithmetic circuits? So here is a quick example. x1, x2, x3 are the inputs to the circuit. It's a directed graph, and the values flow from above to below. Plus, the plus here is the gate that takes x1 and x2 as input and computes its sum. And then it's followed, it gives its output as input to another plus gate, which takes the other input as x3. So this plus gate, the second one here, computes x1 plus x2 plus x3 in this cascaded manner. On the other side, you have a times gate which computes x1 into x3. And if the ring were non-commutative, we'll assume that it's ordered, the multiplication gates take inputs from left to right. So x1 into x3 is x1 into x3, not x3 into x1. And then you add to it the output of this plus gate, which is x1 plus x2. And finally, you multiply the two things coming from both sides and you get this polynomial. And the order for multiplication matters when you're working with the non-commutative domain. There's a weaker model which is also very interesting for us, and that's called algebraic branching programs. So since we don't know how to handle strong models of computation, we always look for easy ways out and look at easy models of computation. So what does this do? It says basically that I can start with so it's the computation model is like a graph, a directed acyclic graph where things flow from left to right. And I can start with S and I can say that I'll take x2, I'll multiply 1 with x2 and go to this node here. And then I can multiply it by x1 and go to this node, and then again by x1 and then again by x1. And that gives me the term x2 into x1 cube. Okay. So for every path in this directed graph from S to T, the start to the final node, I have a path that is labeled by either variables or linear forms. And what I should do is, in this model, multiply everything along that path. If it's non-commutative, the order is important from left to right, and add up all the things that you get along different paths. There is a reason why this model is interesting, and I'll come to that in a moment. But so the polynomial that is computed by this model is what I've written down here. There are so many terms corresponding to the so many paths from S to T. Each path gives a product term like this. And I should say that in the case of the circuit, the size of a circuit is the number of gates in it. You could also count the inputs, they're called input gates if you want. And here the size is just the number of nodes in the algebraic branching program in this graph. Okay. And yeah, this I've already told you. There is another important thing here which we need to keep in mind. So when we have an algebraic branching program, we can associate to it matrices, which basically have as many rows and columns as the number of nodes in this matrix. So this matrix MXI will have 15 rows and 15 columns. A particular row S, the Sth row and the Tth column are important because the Sth entry is going to correspond to what is computed by this polynomial. But what is actually computed? What you do is you take, for every variable xi, you can associate a scalar matrix to it. Namely, you look at the ijth, the ith node and the jth node in this algebraic branching program. And for example, the two nodes that I'm pointing to, the edge is labeled by x2, and let's say this is I and this is j, then the mx2 matrix, the ijth entry, will have the scalar 1 in it, because that's the coefficient of x2. So for every variable, there is a matrix that you can associate to it. And if you give me a monomial, let's say the monomial x2, x1, 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 then you take the matrices mx2 in times mx1 times mx1 times mx1 and look at the stth entry, that will give you the coefficient of x2 into x1 cube and so on. So it's clear. So these matrices are important for us. Okay, moving on. So this is something that I told you, that the determinant, the commutative world has efficient algorithms. In particular, it even has polynomial size algebraic branching programs, as shown by Valiant in 1992, and later Meena and Vinay gave a beautiful algebraic branching program for the determinant. It turns out that the determinant is typical of polynomial size, polynomial degree commutative circuits. That's like the polynomial time analog in the commutative arithmetic world, because they can all be simulated by quasi-polynomial size, n to the log n size algebraic branching programs. Okay. So the determinant is not just interesting because it's ubiquitous everywhere. It's also a complete problem for the class of easily solvable problems in the arithmetic circuit, commutative arithmetic circuit world. In contrast, algebraic branching programs in the non-commutative world are quite weak. You can show, Nizan showed that any algebraic branching program that computes the permanent requires exponential size. N is the size of the permanent matrix. So this is a permanent polynomial, is the permanent of polynomial, the matrix consists, whose entries are all distinct indeterminates, non-commuting indeterminates, xij. Okay. Notice the reason why the commutative, why in the commutative world algebraic branching programs are so powerful is, of course, because of commutativity they can do much more, they can solve the determinant, and they are nearly as strong as circuits. That's what the second line actually implies. Whereas in the non-commutative world, that's not the case. For example, you take this palindrome polynomial, which makes sense in the non-commutative world. Namely, just look at all words of length n over the letters x0 and x1 and look at w times w reverse, okay, and add it all up. It's easy to see that this has small arithmetic circuits, but it requires exponential size algebraic branching programs. And that's actually because of the following reason. So People who have seen a bit of theory of computing or done a course in theory of computation would recall that palindromes are a classical example of context-free languages, whereas which contrasts with regular languages. So just so continuing further, now I'm going to come to the connection to automata theory, the analogy with automata theory. So let me quickly recall for you a very important piece of work of Noam Chomsky, which is the Chomsky hierarchy of formal languages. It's also called the Chomsky-Schutzenberger hierarchy. So it's a foundational piece of work in linguistics, which also deeply impacted computer science. The idea is formal grammars as generational grammars. They generate languages. And so type 3 grammar, so he classified languages depending on the kind of grammars that can generate those languages, with the idea of studying natural languages, of course. And the easiest kind of grammars he could come up with are called type 3 grammars, where it basically says that I can start with something like a noun phrase or a verb phrase, capital A, and I can produce a letter, and now I'll go to a new noun phrase called capital B, from where I can produce new things and so on. But it's a kind of linear structure because I can only produce one thing at a time. And and it turns out that the languages that you could construct using such production rules are called regular languages. And the interesting thing is that they can be recognized by finite automata. So basically, finite automata are like Markov chains, memory-less structures. You see a letter and you go to a state, you don't need to remember what you saw earlier. The state is what matters. And from this state, you can see a letter and go to a fresh state and so on. So you start at a start state and you finish at a final state. All kinds of words that you can generate using this kind of a finite automaton are called regular languages. They are very important in lexical analysis and compilers. So Chomsky's work deeply gave formal structure to the design of compilers, and lexical analysis, basically study of finite automata and regular languages. The next kind of grammar that he defined were type 2 grammars, where you allow production rules, where on the left side you have a non-terminal of a noun phrase or a verb phrase. On the right side you can have a string of letters and so-called non-terminals. So the languages you can generate using such production rules are called context-free languages. And they're basically, the interesting thing is that they can be recognized with using finite automata with a push-down memory. So this is important in syntax analysis of programming languages, for example. And if you turn around this production rule, you can also think of it as a circuit, because whatever is in alpha are things that are coming from below as outputs, and they produce A. Okay, they combine together to produce A. So you can view it in some sense in both directions. I'm being hazy here, but I just want to explain this analogy. The next kind of grammar is what is called context-sensitive grammars, where the context in which a non-terminal is placed is important. So I can replace A by gamma, provided it's in the context alpha beta. And it turns out that, again, there is a computation model which is linear space-bounded algorithms, which are precisely those algorithms that non-deterministic linear space-bounded algorithms, they recognize such languages. And the most general kind of grammar is free for all, and they can essentially capture all what are called recursively enumerable languages. Okay. So see, this is in the infinite domain, and just to go back and explain one point here, I can interpret this picture here, which I explained as an algebraic branching program, as a kind of automaton, because I start with at the state S. If I see the letter x2, I go to this state. Again, if I see the letter x1 and so on. So this word x2, x1 cube is something that this automaton can recognize, can accept. The only difference here in the world of polynomials is that there are also coefficients and they can cancel with each other and so on. Whereas when it comes to finite automata, it's as if we are working over the Boolean ring. The coefficient ring is just the Boolean domain. Okay. And the polynomial is just a collection of words in that case. Okay. But this analogy is very important for the few results that I'm going to show you in the next 7-8 minutes. One very important property that we'll use repeatedly is that there are very nice closure properties that these the classes of languages enjoy. So if I take a regular language and take its intersection with a context-free language, I get back a context-free language. But the intersection of two context-free languages is, alas, not context-free. On the other hand, context-sensitive languages are very robust. They are closed under complements, intersections, unions, everything. So the analogy that really helped us prove the kind of results that I'm going to quickly show you is the fact that algebraic branching programs correspond to finite automata, arithmetic, non-commutative arithmetic circuits correspond to context-free grammars. And there's also an interesting rank characterization of regular languages. So if you take the infinite matrix whose rows and columns are labeled by words, and if you take the entry corresponding to the W1, W2 at W1 row and W2 at column, and if W1 concatenated with W2 is in the language, you put a 1, otherwise you put a 0, then the language is regular if and only if this infinite matrix has finite rank. And the rank of the matrix is actually the size of the smallest automaton for it. And the Nizan rank lower bound argument, I didn't tell you that it's a rank argument, but it is a rank argument. It's like a finite slice of this infinite element. Okay, so what is it in the world of polynomials, non-commutative polynomials, that is an analog of a regular language intersection context-free language being context-free? It's the Hadamard product. So if you give me two polynomials f and g, the Hadamard product of f and g is you take all the monomials and multiply the coefficient of the monomial m in the Hadamard product is just the product of the coefficients of m and f and g. Okay. And the nice thing is that just like the intersection of two regular languages is regular, you can show that the Hadamard product of two polynomials which have small algebraic branching programs of sizes S1 and S2 has size essentially order S1 into S2. Okay. And the other thing is that if F has an algebraic branching program of size S1 and G has an arithmetic circuit of size S2, their Hadamard product has an arithmetic circuit of size order S1 and S2. It's a perfect analogy of the fact that regular intersection context-free is context-free, except that sizes now matter because we are looking at finite objects and the size of circuits and size of algebraic branching programs matter. So these are our tools, and we are going to, there's just one more small thing I want to point out. So if I want to take the Hadamard product of F with P, I can do something very nice. I think of P as given by an algebraic branching program. It has variables x, y, and z in it. I can write down the matrices corresponding to these, the ones that I told you about right at the beginning. And now, if I want to compute the Hadamard product of F with P, all I need to do is, for the variables x, y, and z in the polynomial F, I just substitute these three matrices and look at the 1/4 entry, because 1 is the starting state of my algebraic branching program and 4 is the final state. And that will give me the Hadamard product of the two. So it looks kind of magical, but it's really easy because the polynomial F, essentially monomial by monomial, this algebraic branching program as an automaton is running on it, and its coefficient is going to get multiplied like C1 into B1 is there with the coefficient of the monomial in F. And if a monomial is not present in F, it's going to disappear because this algebraic branching program doesn't recognize that monomial. It doesn't take it from the start to the final state. Okay, good. So I can, that's the reason why I can do something nice with non-commutative arithmetic circuits. If you give me a polynomial f by a circuit and a monomial m, I can find its coefficient by designing an automaton that accepts only that monomial and evaluating the circuit on the corresponding matrices that I just told you about. In contrast, in the commutative world, if you take this polynomial, for example, which is a very simple polynomial, the coefficient of x1 into x2 into xn is the permanent of the matrix Aij. So that's hard to compute. Okay, I think I'm really running out of time, and I've not even started telling you about, so I should at least give you one example. So this is technically the definition of VP and VV for valiant. VP is the valiant analog of polynomial time, and VNP is the valiant analog of non-deterministic polynomial time. So VP just consists of families of polynomials, each of which has a small circuit of small degree, polynomial size and polynomial degree. Because circuits in general can compute exponential degree polynomials, or circuits of size S can compute 2 power S degree polynomials. And the NP valiant class is simply like, you have these extra variables y1 to yrn, and they are like, keeping track of the solutions of the NP problem in some sense. And when you add up over all the values of y1 to yrn over 0, 1, it's like counting all the solutions. And that's what actually the original permanent polynomial corresponds to. And that's the reason Valiant was inspired to define VNP like this, which is a nice definition. Okay. So permanent is in VNP, it's even VNP complete in the commutative world, and determinant is in VP because, for example, of Mina's algebraic branching program for the determinant. And how do you prove something is complete? You need a notion of reductions. I say that if I have two polynomials f and g, g is harder than f if I can easily transform f into g. Okay, because then I can use g to compute f. And the easiest kind of reductions are projections, which are just mathematical projections. You either replace a variable by a variable already used, or you replace it by a scalar. Okay. And it turns out that the permanent is VNP complete with respect to projections. Determinant is VP complete with respect to quasi-polynomial size projections. But in the non-commutative world, things get different and interesting. And I think I'll be able to tell you only one very, very quick thing. A more general notion of reducibility with generalizes projections is possible through matrix substitutions. That's what I call less than equal to mat. And for example, matrix projections are stronger than, matrix reductions are stronger than projections because you can never project G to get two monomials because G is a single monomial. Whereas I can use matrix substitutions and look at a particular entry of the resulting matrix to reduce F to G. And the interesting thing is that not only is the non-commutative permanent VNP complete, the non-commutative determinant is also VNP complete. The first one is with respect to projections. The second one has to be with respect to matrix reductions. You can't do it with respect to projections because we have a transfer theorem which says that if something in the non-commutative world was complete with respect to projections, then you can take it back to the commutative world. And we know determinants are easy in the commutative world. But with respect to matrix reductions, it is VNP complete. And how do we do it? So we want to reduce the permanent to the determinant. So that means that you have to remove the sign. But how do we compute the sign of a permutation? And I need to use matrices as substitutions. That means I really only have the power of automata with me. And automata cannot keep track of bijections, leave alone compute the sign of a permutation. So, but it turns out that we can reduce the permanent polynomial to the 2n by 2n determinant polynomial in the non-commutative world. And the idea is very simple. We will only look for certain very nice permutations. So for every permutation pi in Sn, we will define a permutation in S2n which looks like this. Pi1 n plus pi 1, pi 2, n plus pi 2. So this is the ordering. So pi 1, pi 2, pi n is the permutation in Sn that's given to me, and I expand it out into a permutation on 1 to 2n. And the nice thing about this permutation, rho of pi is a permutation on 1 to 2n. They all have the same sign, and the sign is that of rho of the identity permutation. And so it turns out, therefore, that I just need to, my automaton needs to just recognize monomials of this type. But still, how do I know that I1, I2, In forms a permutation on 1 to n? I don't need to worry about it because the determinant polynomial already takes care of that. So when I take the Hadamard product, this will make sure that I pull out only the permutations which are of the form rho pi, and the determinant will take care that everything is actually a permutation. So, and the sign is the same, so the sign disappears and we get the n by n permanent. I think I've really run out of time, and I just want to say that the analogy continues. So if I want VP completeness, now determinant is hard. So what is VP complete in the non-commutative world? You don't have to look far. Automata theory helps out. Dyke languages. So you can define Dyke polynomials and use the Chomsky-Schutzenberger theorem, which talks of the hardest context-free languages to show that the Dyke polynomial is VP complete. And we can create, using context-sensitive languages, we can create more VNP complete problems, which again are analogous, not look like permanent or determinant, but really come from the formal language, from the theory of computation setting, Hopcroft and Ullman setting. Okay. I will not have time to talk about the polynomial identity testing problem, but here too I must say that automata theory helps out in a major way. I will just rush towards the end and say something about a bunch of new results on what is the rational identity testing problem. So dealing with inverses in the non-commutative world is a totally different thing than dealing with inverses in the commutative world, because the universal free skew field has very complicated objects in it. And so you're given a rational formula, non-commutative rational formula, and you want to test if it's identically zero. So for example, just to give you a flavor of what inverses can, how messy they can look in the non-commutative world. So this is actually equal to zero, and that's called Hua's identity. So you can't simplify a non-commutative rational expression as f by g, which you can do in the commutative world, because you can move around divisions. Here, whether you're dividing on the left or right matters, and things are harder. And it turns out that if you're given a rational formula explicitly, you can do identity testing in deterministic polynomial time. Identity testing means you're given an expression, you want to test if it's identically zero. It's connected to lower bounds. No time to get into that. But the other related question is black box identity testing, where you don't see the formula, you can only evaluate it. So for example, if I put inside a black box a degree n univariate polynomial, and I want to find a point where that polynomial is non-zero, I'm only allowed to evaluate that polynomial. What will I do? I know it's degree n, so I'll take 1, 2, 3 up to n plus 1. I'll evaluate it at all these n plus 1 points. I know at one of these points it has to be non-zero if the polynomial is non-zero. But can I do it in the multivariate setting? That is the harder problem. Okay, how do I efficiently do it in the multivariate setting? So the polynomial is, the rational expression is inside a black box, and how do I deterministically check whether it is the zero expression or not? We can only do it in the special case of inversion height 2, and we only get a quasi-polynomial time algorithm, n to the log n time algorithm. And the efficient de-randomization is open. Just finally, one more result, connecting hardness to randomness. So it's known in the commutative setting that if you assume that the permanent polynomial is hard, then you can get reasonably efficient algorithms for polynomial identity testing. You can so-called de-randomize polynomial identity testing. And we could do something similar, assuming that polynomial identities in the non-commutative world have exponential algebraic branching program complexity. Okay, I think I've taken up more than my time. Thank you.